All right, everybody. So, welcome back. I hope that everybody's doing well and that your first week of classes is going well as well. So, when we left off last time, this was the model that we were kind of working on, which we had called the uh, particle nature of matter. Right? And this particular model allowed us to describe three different variables. Those three variables were mass, which is the amount of stuff, right, that a substance contains, right? And we can just count the number of particles within this and the size of the particles and things like that. And then this model also allows us to describe the volume, which is the amount of space that a substance occupies. And then the last was the density. All right, which was the relationship between the mass and the volume, right? So the amount of stuff in a given space. All right, so now we're going to see if this model fits with our next concept or if we need to modify this particular model. Model over here, this particular model does not account for the movement of the particles. So we'll have to modify that. So to do this, we're going to have the example that we're going to use is your olfactory nerves, right? Which are way up into your nasal cavity. And the function of the olfactory nerves are to provide the sense of smell. And so the way that they work is a compound of various different types. Like let's consider like a Febreze aerosol spray or something, right? We'll just think of that right now, right? And so the way that this works is that a specific compound will then go up into your nose. It will attach, right, to these olfactory nerves, and then they will then send a signal to the frontal part of your brain that will say, okay, something is attached to your olfactory nerves that has this particular identity, and then your brain interprets that as a specific smell. Okay? And so one of the ways to really picture, but first for this is, let's say that you're driving down the road and all of a sudden you smell the smell of a skunk, right? So what's really happening, right? And I'm sure most of you understand that the way that the skunks work is for a defense mechanism. They emit like a spray out of glands in their anus, right? And so what's happening then is that tiny, tiny, tiny little particles, droplets, right, are then dispersing into the air. And every once in a while, if you're driving by, like where a skunk has sprayed or it's been hit by a car or something, one of those tiny, tiny, tiny little particles will move up into your nose as you're inhaling and attach to your olfactory nerves, right? So what this tells us then is that if that's possible to happen, because you're not sitting there, like, I guess sometimes you could be, but like if you're just driving your car, you're not just sitting there having a skunk spray these things up into your nose. No, those tiny particles are moving, right? So this is evidence then that particles move. All right, and if we go, let's start thinking about some things that may cause particles to move at a different rate. Okay? And some of those things could possibly be airflow. Some could be temperature. Right? Some could be air density. And so what we're going to really focus on is to see if there's a relationship between temperature and how fast these particles move. All right. So I will go ahead and pull up another video here and see if we can demonstrate this. Okay, so in the left container, I have very, very hot water. as you can see with the steam. And in the right container, I have very, very cold water, right? And so the particles of the water are very difficult to see, but if we just add a little bit of food coloring, then we can see the particles and how they move, right? And if we just give it a moment here, what you should be able to notice is that the food coloring in the hot water is dispersing much faster than the food coloring in the cold water, which means that those particles must be moving faster. So what this means is that we're going to now have to modify our particle model that we had described earlier. Okay, so now that we see that temperature does affect the rate at which particles move, we then need to modify our model that we have. So let's see if there's a way that we can not only represent the fact that particles move, but also that temperature affects that. So let's go ahead and start with a simple particle diagram. And we'll say that these are the particles that were in the cold water, right? And then we will move on to another particle diagram, and we'll say that these are the particles that were in the hot water. So the easiest way that we can use to represent particles moving at different speeds, right? We know that they move, is just by attaching arrows to the particles and saying then that the length of the arrow is a representation of how fast the particles were moving, and also then the temperature, right? So particle speed is dependent on temperature. Okay, so now let's focus at just this particle diagram right here, and we'll just focus on one specific particle for now, and we'll look at this one right here. All right, so we've indicated that it's going to move, right? And let's assume that this is a sealed container, okay? So we've now said that this is going to move, right? And if we follow the path of this particle, it's either going to run into this particular particle here, or it's going to hit the wall of the container. Okay, now if we think of all of the particles, the 4 particles that are in here, right, they're all going to do the same thing, right? And so we have a definition for these particles running into the sides of their container, and we call that pressure. Okay, and pressure is defined as the rate at which particles collide with the sides of their container. Okay. And there are various different units that are used in terms of pressure, including PSI, which is pounds per square inch, right? You've probably heard this used in terms of things like your car tires. There are kilopascals. There are what we call torr or atmospheres. Okay, so there are various different measures, and I will give you here in a little bit the relation between each of those measures. All right, so we had just talked about how we define pressure And we'll kind of go over that again here today and the conditions in which we can talk about that. And we're also going to talk about how we measure pressure, right? And so to do this, we're going to use what is called the kinetic molecular theory, right? And it's a single set of descriptive characteristics of a substance known as what we call the ideal gas, okay? Now, all real gases, such as oxygen gas or carbon dioxide gas or water vapor, right? They all have their own unique sets of descriptive characteristics. But because there are such a large number of known gases in the world, the task of trying to describe each one of them individually would be arduous, right? It wouldn't be efficient in trying to just explain how gases actually work. So in order to simplify this particular task, the scientific community has decided to create an imaginary gas that approximates the behavior of all real gases. So in other words, the ideal gas is a substance that does not exist, right? And the kinetic molecular theory describes that particular gas. So while the use of the ideal gas in describing all real gases means that these descriptions of all real gases will be wrong, the reality is that the descriptions of real gases will be close enough to correct any errors, okay? So here are the 5 postulates or assumptions that we make when we are talking about gases. The first one is that the gas consists of particles with a defined mass, right, because they are a particle, and 0 volume. Okay? The gas particles travel randomly in a straight line motion where their movement can be described by Newton's 3 laws. Okay? All collisions involving gas particles are what we call elastic, meaning that the kinetic energy of the system is conserved and they just bounce off of one another. Okay, they don't stick to one another. Right, they're elastic, and there are no attractive or repulsive forces between the molecules or the walls of whatever container the gas is in. And that the gas phase system will have an average kinetic energy that is proportional to temperature, right? So again, this is talking about what we had just described a little bit earlier, that the temperature is relative to the speed of the particles. So what is pressure? We just defined this just a few moments ago as the rate at which particles collide with the walls of their container. Okay. And some of you have probably heard, if you watch the news, I watched the news like crazy when I was a kid. I still do, right? But anyways, if you pay attention to the weather, a lot of times they talk about this atmospheric pressure, right? And so the atmospheric pressure is the force of air particles on the surface. Right? It's just the weight of all of those air particles on top of the surface. So thinking in terms of air molecules, if the number of air molecules above a surface or above you, all right, if there are more molecules, right, to exert a force on that surface, and consequently then the pressure will increase, right? So if there's more stuff on top of you, then that weight of all of those particles you're going to feel that, okay? The opposite is also true. So where a reduction in the number of air molecules above a surface will result in a decrease in pressure. So there's a couple of demonstrations that I do when I'm in a face-to-face class, and I'm going to kind of describe those to you here. Okay. And they're all related to atmospheric pressure. So if you take a 2-liter bottle, now please, please, please forgive my drawing capabilities here, but if you take a 2-liter bottle, right, and you fill it up to some certain level, and there's a cap on top of it, right, and you poke a hole in the side of it, and you can try this at home, nothing will happen, right, even though there's a hole, right, in the side of it, right. I usually use like a push pin or something to do that, right. But if you take the cap off, right, then that water starts to pour out of the 2-liter bottle. And the reason is that you're now having all of those air particles. So there were air particles hitting this, bouncing off of there, so on and so forth. But now those air particles are able to get in there, and they're pushing down on this surface of the water, forcing the water out. Okay. The second demonstration that I usually do is this can crush demonstration. And so if you put a soda can on a hot plate, okay, like so, and it's open, there's nothing inside of it, okay, and you heat it up so that it's really, 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 really hot, and then you put it upside down, okay, into a bath of ice water, okay, the can will crush, okay, and the reason is that on this hot plate right here, okay, the particles inside of the can are moving super, 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 super fast, right? And on the outside, okay? When you stick it into the ice water bath, right, the particles then on the inside of the can start moving. So we'll draw a diagram here. The particles on the inside of the can start moving really, really slow because of the ice water. But the particles that are right on the outside of this can are still moving much, much faster, okay? And so it ends up crushing the can. And a couple of demonstrations that, I usually do when I have a face-to-face type of class. All right, so now let's start talking about how we actually measure pressure, atmospheric pressure, and then general pressure. So atmospheric pressure is measured with an instrument that is located to the right here called a barometer. All right, which is why atmospheric pressure, if you watch the weather, is also referred to as barometric pressure. All right, and then atmospheric pressure then pushes down on this plate right here, or a container, right, that contains a lot of mercury, okay, so it pushes down on that, causing the mercury then to rise inside of this tube. So the atmospheric pressure pushes down on the surface of the mercury in the pan, which causes the mercury inside the tube to rise, right? And the greater the pressure, or the more particles that are pushing down on here, okay, so the greater the atmospheric pressure, the higher, right, the column of mercury will rise in this particular column, right? And the height of the mercury, so the height like so, right, in millimeters is used to express the amount of atmospheric pressure, right? So the barometer measures atmospheric pressure in millimeters of mercury. So we write that as millimeters of mercury. Hg is the symbol for mercury, right? And standard atmospheric pressure at sea level in millimeters of mercury is 760 millimeters of mercury. All right. So barometers essentially are measuring the amount of force of the air molecules pushing down on that mercury column. So at higher altitudes, let's say that we're on top of Mount Everest, there are less air particles. Okay, therefore, and I like to draw a diagram here that actually relates the two. So I'm going to come over here to the side, all right, and okay. So let's say that this is me. Again, please don't judge my my drawing capabilities. And I am in Escanaba, right, which is about 500 feet in elevation, right? And that this is the top of Mount Everest. And off the top of my head, it's somewhere around 30,000 feet in elevation, right? And so there's all of these air particles, right? And they're moving, right? Right? And okay, and so here I am on the top of Mount Everest, right? So you can see that there are more air particles on top of me when I'm in Escanaba than when I am at the top of Mount Everest. So therefore, the pressure is going to be higher when I'm in Escanaba than when I am at Mount Everest. So if there are fewer air molecules, then there's less weight force pushing down on the mercury column, and the result is a lower pressure reading, right? So you can see that this is what the pan looks like at sea level, or close to, in Escanaba, right? So there's pushing really, really hard down on this pan and pushing more mercury up, whereas here it's not pushing quite as hard because there just aren't as many particles, right? And so it doesn't push the column up quite as high. All right, so another way other than a barometer to measure gas pressure is what we call a manometer. Usually in my classes, I go over how a manometer works. It's really no different than a barometer, but I'm not going to assess you on any of these problems, so I'm not going to include that in this particular discussion. All right, now let's talk about the units of pressure. We've already mentioned a couple, but at standard conditions, the height of mercury in a column, we already talked about that, is 760 millimeters, right? That height is used as the basis of another unit of pressure, which is called an atmosphere, which was noted as ATM. All right, millimeters of mercury is also called torr. Okay, and pressure is also defined as a force per unit area, right? This is a physics type of deal. So therefore, another unit of pressure is the metric Pascal, right, which is newtons per meter square. So, and then if you have 1,000, if you have 1,000 of anything, we just put the word kilo in front of it. So if you have 1,000 pascals, you have 1 kilopascal. Now, in the English system, which we had discussed just a little bit ago, we use pounds per square inch, right, which is PSI. Okay, so we can then use this information here to do some conversions, right? So I forgot to put this particular conversion chart on the next page. So you may just, copy this in some way, this particular chart right here, and you can write it down. But these are essentially going to be your conversion factors, right? Remember from the dimensional analysis discussion that we did earlier, okay? So there are then a few practice problems that you can do in terms of converting units of pressure. So I would pause and I will go ahead and work out all of these problems. You can try them on your own and then come back and get the correct answers. And I promise a few of you noticed that I made a mistake last week in the scientific notation notes. There's one particular problem. I didn't move the decimal enough places. So please, if you notice something that you just don't think is right and I messed up, go ahead and let me know. So, all right, so in the first problem, we're going to be converting 5.5 atmospheres, all right, into millimeters of mercury, right? And if you saw on our conversion chart, 1 atmosphere is equal to 760 millimeters of mercury. So we can cross out our atmospheres, multiply our fractions, and we get 4,180 millimeters of mercury. Now the next one is asking us to go from 550 millimeters of mercury to pascals. Now if you notice, we don't have a direct conversion factor from millimeters of mercury to pascals. So we will have to use two conversion factors, right? So we can go from millimeters of mercury to atmospheres, and then atmospheres to pascals. All right, and so we can cancel our units of millimeters of mercury and our units of atmospheres, which leaves us with just the units of pascals, and you can multiply your fractions across, and you should get something like 73,000 to 327 pascals. All right. The next problem is going from 25 pascals to atmospheres okay. We can eliminate our units of pascals, and what we get if we write this in scientific notation, so we don't have to write all those silly zeros, is 2.46 times 10 to the negative fourth atmospheres. Okay. And then the last problem is we are going from torr to PSI. Again, we don't have a direct conversion factor for that, so we will go from torr to atmospheres, and then atmospheres to PSI. Okay. And that will equal 3.87 PSI. All right. So that is how we measure pressure and the units of pressure. Now, if we go back to our definition of pressure and look at the particle diagram of it, so we can start thinking about what are some variables that may change the rate at which these particles collide with the sides of their container, right? To see if we can start to identify some variables that relate to pressure, right? So if we look at this particle diagram, there are a couple of different variables that we can test that may change the rate at which the particles collide with the walls of their container, and we'll be discussing that next. Okay, so in the previous video, I had talked about that there would be some variables that we could look at and to see how they affect the pressure of a system. So we're going to go ahead and take a look at some of those specific variables. So the first variable that we're going to look at has to do with pressure and volume. So in this instance then, the temperature of the system and the number of particles are going to be held constant, right? And so the easiest way to look at this then, so what we're looking at then is the volume, the variables of volume and pressure. And actually, sorry, I should put that up here, pressure and volume, right? So let's say that we have a substance that looks like this, okay? And let's say that we change the volume to something like this. If we work off of our definition of pressure as being the rate at which particles collide into the walls of their container, then we should be able to see that as the volume increased here, that the rate at which the particles collide with the walls of the container or the pressure are going to decrease. So we can graph this. So if we graph this with pressure being our on our y-axis and volume being here, we would see that as the volume increases, the pressure decreases. Right? So as the volume increases, the pressure decreases. And then the inverse is true too. So as the volume decreases, right? So if we were going from the larger volume to the smaller volume, the pressure would then increase. So volume is decreasing, the pressure is increasing. Right? And so this is what we call an inverse relationship. So volume and pressure are inversely proportional. Okay, so here are the important things that you're going to want to know about each of these particular relationships. Okay, the name, not important to me. The relationship, very important. The ability to draw the particle diagrams so that you can represent this in a model, very important. And then knowing what the graph of that particular relationship looks like is also going to be very important. All right, so let's go ahead and look at the next relationship. And in this relationship, we're now looking at temperature and pressure. So therefore, we're going to keep volume and again, number of particles constant. Okay, so let's look at this. So let's start with, a particle diagram. Okay. With slow-moving cold particles. Okay, and then let's increase the temperature. And remember, temperature is related to speed. Okay, so again, if we go off of our working definition of pressure as the rate at which particles collide with the walls of their container, you should see that the walls of the container with the faster-moving, hotter particles is going to be greater. Right? So we can make a graph of this. Now we're going to look at two separate graphs. All right? If we look at this relationship between pressure and temperature in degrees Celsius, the graph appears like this. Okay? Where this point on the graph right here represents 0 degrees Celsius, right? But we still have particles moving. We still have a pressure, right? If we extend this graph this way, we go to a point right here, right? And what the particle diagram right there would look like, okay, is when there's no pressure. Well, the only way to have no pressure and particles is if those particles have no movement, okay? So what is that temperature then in degrees Celsius? So this would be 0 pressure, okay, because there's no movement, right? The particles are not colliding with the walls of their container, right? Well, theoretically, right, according to this graph, this point on the graph would have a number, and that number is negative 273 degrees Celsius, okay? And that would be the temperature at which particles would no longer move, right? So if we then call that that temperature absolute 0 or 0 Kelvin, all right? And so if we then plot the pressure versus the temperature in Kelvin, right, we have a graph that looks like this, right? Where 0 Kelvin represents, this point right here represents this instance right here. So what this gives us then is a equation that we can use then to get to the temperature in Kelvin. So the temperature in Kelvin is equal to the temperature in degrees Celsius plus 273, okay? And we get that from observing this particular graph right here, Okay. Now, the other thing that we should see in this relationship is that as the temperature increases, the pressure increases, right? So as the temperature increases, the pressure increases. And as the temperature decreases, the pressure decreases. Now, it's important while we're working on gas law problems that we use this graph as our basis and not the graph that is the relationship between pressure and degrees Celsius. So that means that in any gas law problem, you need to convert your temperature in degrees Celsius to Kelvin using this formula right here, right? And this relationship then are directly proportional, right? As one goes up, the other goes up. As one goes down, the other goes down, right? So let's look at our next relationship. And this one now has to do with pressure and number of particles, right? So in this instance, then we're going to keep volume and temperature constant, okay? So let's look at this then. If we have a container that has 2 particles at a specific temperature and a container of the same size at that same temperature, but it has more particles, then you should see that the one that has more particles, the walls of that container are going to get hit more often. Okay, so the pressure is going to be higher. So we can then graph this as well, like so. So as the number of particles increase, pressure increases. And opposite of that, as the number of particles decrease, pressure also decreases. And so this is also a directly proportional relationship. All right, now the next one, we're going to keep number of particles and pressure of the gas constant, okay? And one way of picturing this is a balloon, okay? We can keep the pressure inside of the balloon constant and the number of particles. So I'm not talking about a balloon. One way that I usually demonstrate this particular law is I will take a flask and I will wrap a balloon around the top of the flask, okay? And I'll put it on a hot plate, okay? And what I usually see is that the flask, while it's on the hot plate and the balloon, right, the volume inside of the balloon increases, right? So let's look at this in a particle diagram now. So if we have slow-moving particles and we have an expandable type of substance like a balloon, okay, as the temperature increases, that's going to push that balloon to a larger volume, okay? And again, because we're dealing with gases, we need to make sure that we are talking about the temperature in Kelvin. So as the temperature increases, volume increases. As the temperature decreases, volume decreases. Okay. And so these are also directly proportional. All right. So now let's look at how we can use this information to make some predictions about gases. So, I'm gonna go ahead and I'm gonna give you right up top here the procedure that I'm gonna use in handling these problems. Let me just find my notes here. And so on each of the problems below, start with the given pressure, volume, temperature, or number of particles. Then make a decision as to how a change in pressure, volume, temperature, or number of particles will affect the starting quantity, right? And then multiply by the appropriate factor. Draw particle diagrams of the initial and final conditions, as well as sketching a graph of the specific relationship. So there's a lot to kind of take apart in there. And I'm going to help you work on doing that. Okay. So there's a tool here, this little IFE table, initial, final, and effect, right? And this tool is only useful if you understand exactly how to use it. So I'm going to give you a kind of a step-by-step process up here of how to do this. So step number 1 is going to identify the graph of the law or laws that are involved in the specific problem. Okay. Step number 2 is going to be to draw particle diagrams of the initial and final conditions. Okay. Step number 3 is going to fill out the table with the information that you have. Okay. Step number 4 is going to be to fill out the effect box below your question mark. All right, I'll go through that. It's very important that that's the only effect box that you fill out. Step number 5 is going to be to arrange your conversion factors based on the effect box. And step number 6 is to multiply your conversion factors by the given amount. All right, so let's look at this step by step in question number 1. So a sample of gas occupies 150 milliliters at 25 degrees Celsius. What is its volume when the temperature is increased to 50 degrees Celsius? So in this instance, it also tells us that pressure is held constant, so we don't need to worry about that, and number of particles is held constant. So we have now a relationship between temperature and volume. Okay, so let's go ahead and get a graph of step number 1 says graph of the law. So temperature and volume graph looks like this. Remember, our temperature has to be in Kelvin, and it looks like that. All right. Step number 2 is to draw particle diagrams of the initial and final conditions, right? So initially we have particles at 150 milliliters and 298 Kelvin. Notice that I converted that temperature in degrees Celsius to Kelvin. It is so important that you remember to do that. Okay. Now, we have an unknown volume, but we know that the temperature has increased to 323 Kelvin. Okay. So our temperature has increased. Right. So let me show you a little trick on how to do this with the graph. Okay. And I'm sorry, step number 3 now is to fill out the table. So we'll do that, and I'll teach you how then to use the graph. So let's fill out this table. So initially, we have a temperature of 298 298 Kelvin and 150 milliliters. Okay. Our next temperature is now 323 Kelvin with an unknown volume. Okay. Now, it says to fill out the effect box below the question mark. All right. So we're only going to fill out the effect box right here. Okay. So we're not going to use this part. So now let's look at the graph and see if that can help us with some information on what the effect is going to be of this change in temperature on the volume. All right. So let's just put some points on the graph. Let's put a point right here. I'm going to use a different color. So let's put a point right here. And that's going to represent 298 Kelvin, right? And 150 milliliters. Okay, which are our initial conditions. Okay, now our new temperature is 323 Kelvin. So that's like right here. And we don't know what that volume is, but we know based on our graph that it is going to be greater than 150 milliliters. So what we can then say is that the volume is going to increase because of a change in temperature. Okay. So we've now filled out our effect box below the question mark. So now we're going to look at doing some dimensional analysis. All right. So we're going to start with our given, which is 150 milliliters, and put that over 1. Now we need to arrange our temperature conversion factors right here in a way that is going to cause this quantity of 150 milliliters to increase. So our options are 298 Kelvin over 323 Kelvin or 323 Kelvin over 298 Kelvin. Now, if we multiply this 150 milliliters by this number right here, right? Simple mathematics would show us that this number of 150 milliliters would actually go down. And we don't want that, right? So what this effect box essentially tells us is exactly how to arrange our conversion factor. It tells you where to put the larger number in your conversion factor. If the arrow is pointing up, like it is here, you want to put the larger number from your temperature on top. Okay, and if it's pointing down, then you would want to put your larger number on the bottom. Okay, and we'll look at lots of examples here. So we would want to use this conversion factor right here, which is 323 Kelvin. Oh, geez. 323 Kelvin over 298 Kelvin. All right, our like units would cancel out, and we would end up with 163 milliliters when we multiply our fractions. Okay, so this is the correct answer to this particular problem. Let's go ahead and look at the next problem, and we're going to use the exact same set of instructions. Okay, the pressure in a bicycle tire is 105 psi at 25 degrees Celsius in Fresno. You take the bicycle up to Huntington, where the temperature is -5 degrees Celsius. What is the new pressure in the tire, right? And it tells us here that volume and number of particles are held constant. So we're looking at a law that has a relationship between pressure and temperature. So pressure and temperature in degrees Kelvin. And we know that that is a direct relationship. So now let's look at the particle diagrams, right? So we have a particle diagram in Fresno of 298 Kelvin and 105 psi. Okay. We have a constant volume and constant number of particles, and what we do know is that the temperature is going down to 268 Kelvin. We don't know what the pressure will be, so we know there are a couple of things you could look at, right? According to this particle diagram right here, it shows that the pressure is going to decrease, right? So let's go ahead and fill out our table, and we'll look at it on the graph as well. So our initial temperature is 298 Kelvin, and our pressure is 105 psi. Our new temperature is 268 Kelvin, and we don't know what the new pressure is. We're going to go ahead and cross this out because the only effect box that we fill out is below the question mark. And then we have kind of already shown that the pressure is going to go down because of temperature, but let's look at it on the graph as well. So we start out at with a point at 298 Kelvin and 105 psi. Right, we know that we now have a new temperature of 268 Kelvin. Well, we can easily see then that the pressure is going to go down because of the change in temperature, right? So, again, what this effect box tells us is how to arrange our conversion factors. So we have 105 psi over 1. It tells us to put the larger number on the bottom in our conversion factor. So 268 Kelvin and 298 Kelvin. And we can multiply our fractions, and what we get is 94 psi. So now this one, the trickier part about this one is that it doesn't tell us what the constants are, but we can pull that information out of the question. Okay, so it says, what would be the new pressure if 250 centimeters cubed of gas at standard pressure? Just to let you know, standard pressure is either 1 atmosphere, 760 millimeters of mercury, is compressed to a volume of 150 centimeters cubed, right? So what we're looking at here is a relationship between pressure and volume, right? We've got pressure right here and volume right here, that particular change there. So we know that then temperature and number of particles, right, are going to be constant. Okay, so let's go ahead and get a graph of this particular relationship. Remember, pressure and volume are an inverse relationship. Okay, and we're starting out with a volume of 250 centimeters cubed. And at that instance, it's at standard pressure, which is 1 atmosphere or 760 millimeters of mercury. It doesn't matter which one you choose. 1 is just a much easier number to work with mathematically than 760, so I always choose the atmospheres when we're talking about standard pressure, right? We know now that the volume is going to decrease, right, to 150 centimeters cubed, right? Now let's put some particles in here, right, at the same temperature, right? Temperature is not changing. And we want to know what the new pressure would be, okay? So you should be able to just see this relationship from these particle diagrams, right? That if we put these particles into a smaller container, that the pressure is going to increase, or the rate at which they hit the walls of the container are going to increase. But let's look at how we would do this graphically as well. So initially, our volume is 250 centimeters cubed, and that is 1 atmosphere, right? Our volume decreases to 150 centimeters cubed, so that would be somewhere like right here, which we know then that that is going to be an increase in the pressure. So let's go ahead and fill out our table. We've got 250 centimeters cubed, and that's at standard pressure or 1 atmosphere. The volume changes to 150 centimeters cubed, and we want to know what the pressure is, right? What we've already now demonstrated is that the pressure is going to increase due to a change in volume, right? So we can start with our given of 1 atmosphere over 1 times a conversion factor that is going to cause it to go up. So our larger number needs to be on top. So 250 centimeters cubed over 150 centimeters cubed, right? So our units of centimeters cubed cancel, and we multiply and we get 1.67 atmospheres, right? So what happens if multiple variables change, which is what we have in this particular problem? This is when the effect box is really, really, really big. Okay, so what would be the new volume, right? That part of the question, right, tells you you're looking for volume, right? If 250 centimeters cubed of gas, 250 centimeters cubed of gas at 25 degrees Celsius, right? So that's 298 Kelvin. And 730 millimeters of pressure, 730 millimeters of pressure, were changed to standard conditions of temperature and pressure. So I've already told you that standard pressure is 1 atmosphere, or 760 millimeters of mercury. Standard temperature is 0 degrees Celsius or 273 Kelvin. Okay, so we're going to change this now. And so what that means then is we're holding the number of particles constant, right? So we are changing to standard pressure, which is 760 millimeters, and 273 Kelvin. Now, when you have multiple variables changing, a particle diagram doesn't really do you any good, and you really need to rely on the graphs, right? So we know that we now have 2 different graphs that we have to look at, both related to volume. So how does a change in pressure change the volume, and how does a change in temperature change the volume? So we'll look at our first graph, which will be pressure and volume. Okay. And our initial volume, our initial pressure is 730 millimeters, and that corresponds to 250 centimeters cubed, right? We're going to increase the pressure to 760, right? Which means then that the volume must have decreased to some number. So we know then that the volume is going to decrease because of a change in pressure, right? So that tells us how to arrange our pressure conversion factor. But now we have to look at this relationship between temperature and volume. So volume and temperature in degrees Celsius, in Kelvin, looks something like this. So if we start out with a temperature of 298 Kelvin, okay, that is associated with the volume of 250 centimeters cubed, right? And we're going to decrease the temperature to 273 Kelvin, right? And so what we can see then is that that is also going to make the volume decrease. So we are also going to decrease the volume because of a change in temperature. So that tells us now how to arrange this conversion factor. So we will again start out with our given 250 centimeters cubed over 1 times our first conversion factor that is going to cause the volume to go down. So that means 730 millimeters of mercury over 760 millimeters of mercury. Multiply that by our second conversion factor that is going to cause the volume to go down. So that would be 273 Kelvin over 298 Kelvin. Right? So our millimeters of mercury will cancel, our Kelvin will cancel, and we can multiply across, which would give us 220 centimeters cubed. So that would be the new volume if all of these changes occurred with an ideal gas. All right. Our last question here. So a closed flask of air at 0.250 liters contains 5 puffs of particles. The pressure probe on the flask reads 93 kilopascals. A student uses a syringe to add an additional 3 puffs of air through the stopper. Find the new pressure inside the flask. Notice that nowhere else do they tell us any volume, right? So essentially the volume is not changing, right? And neither is the temperature, right? So really what we're looking at here is a relationship between pressure and number of particles. So let's look at that graph. Remember that is they are directly proportional, right? And so now let's look at a particle diagram. So we're keeping temperature and volume constant. Right? I guess I could draw 5 and then 3 more. Maybe I'll do that. I'll change this so that it's exactly how the problem is. All right, so our initial condition, I'll have to make it a little bit bigger. So our initial condition is we have 5 puffs of particles. We'll just say that there are 5 total particles. Right, so we know we have 5 particles, right? And we have a pressure of 93 kilopascals, right? We're not changing the temperature of the volume. We're just adding 3 more puffs of particles, or 3 more total particles. So 1, 2, 3, 4, 5. So there's our original 5. We're going to add 3 more. So what you should see then is that the sides of the container, this has 8 particles now. And we want to know what the pressure is, right? But you should see that based on this, that the pressure is going to increase, or the rate at which the sides of the container get hit by particles increases, right? So let's go ahead and fill this information in our table, and then we'll look at the graph. So we start with 5 puffs of particles, and we end with 8. Our initial pressure is 93 kilopascals, and we want to know what the new pressure is going to be. All right, so let's look at this graphically then. When we have 5 puffs of particles, all right, we have a pressure of 93 kilopascals. Right, when we add 3 more, we now have 8. And we want to know what the pressure is going to be, so we can see that it is going to go up. So the pressure is going to increase because of a change in the number of particles, right? And so again, that tells us how to arrange this conversion factor here. So we'll start with what we were given of 93 kilopascals over 1. It needs to go up, so we need to arrange it so that it will go up. 8 particles over 5 particles, right? And multiply across, and we get 149 kilopascals. All right, so that's the end of the gas law relationships. Please let me know if you have any questions.